Hey everybody, welcome back to another round of astronomy. Yeah, let's get going. We're going to continue on our ideas about celestial dynamics. And in particular, we're going to talk about the seasons and the consequences or why the seasons occur. Okay? Number one, okay? I will start here and I'll probably re-emphasize it a couple times throughout the course of the lecture. Okay? The seasons are not due to the Earth being close or far away from the sun. The common misconception is that seasons occur because the Earth is closer to the sun. The Earth is closer to the sun, it must be summer. The Earth is further away from the sun, it must be winter. Oh, nay, nay. That is not the reason that the seasons occur. Okay? So I'll say that first. Let's get an idea about why the seasons do occur. So I'll start off with this. Say for a moment that it is raining sunlight. Okay? So sunlight is falling from the sky and we have a mission. We have a solar panel that we would like to orient such that it catches as much sunlight as possible. If you don't like this scenario, fine. Let's say it's raining money and you want to catch as much money as possible with a cup. Okay? So it's raining money, raining money. Okay? How should I orient the cup to catch the most money as possible? You got it? Yeah, good, 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 good. If we're trying to catch sunlight with a solar panel, we do not want to hold the solar panel such that it is such that it does not catch any of that sunlight. We want to angle it so that the surface is perpendicular to the direction that the sunlight is coming in at. Okay? Good so far? And you've probably noticed this already. If you drive by a solar farm, or if you see somebody that's taken the time to install solar panels on their roof, you'll notice that they commonly are not placed flat against the ground. Usually they are set up at some sort of angle. That angle is not just aesthetics or arbitrarily chosen. That angle is to make sure that the solar panel is pointing directly at the sun. Catch as much light as possible. Okay, you ready? Yeah, good, good, good. Okay, so the next question I have for you. Let's say for a moment that we have solar panels at 3 different locations. We'll say Quito, Ecuador, Raleigh, North Carolina, and let's go for the North Pole. So Santa's trying to be more energy efficient. Okay? Question for you. Which one's going to collect the more sunlight? You got it? Yeah, good, 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 good. So we're taking this idea about the solar panels being angled and we're going to apply it to these 3 locations on the Earth. Well, because of the Earth being round, right, those solar panels are going to naturally be angled. If I place them flat on the ground, they're going to be naturally angled at different orientations. Okay? And so we can see from the picture that Quito is going to collect the most sunlight, then Raleigh, then the North Pole. Okay? So we even can rank them. Okay? So the first idea, the Earth is round. Okay? And because of that, the solar panels are naturally going to be angled. Some are going to be facing towards the sun more, some of them not as much. Okay? Let's say that it's a bright sunny summer day and you're getting ready to go outside. Okay? What color of shirt are you going to wear outside on a bright sunny day? Yeah. Generally in the summer, we are going to choose lighter colors. Okay? Why is that? Darker colors absorb more sunlight, and because it absorbs more sunlight, they tend to be at higher temperatures. Okay? It tends to be really hot. If you make the mistake of wearing a black shirt on a hot summer day in Hanover, Indiana, you are going to broil. Okay? So the idea stays the same here as well. The solar panel, the area where it's going to receive more sunlight, is going to naturally be at a higher temperature. But wait, there's more. That's only half of the story. You ready for the other half? Okay, good. Let's hop in our spaceship. Okay? We're going to hop in our spaceship and we are flying out now so that we're on the ecliptic plane. The line, or excuse me, the plane defined by the orbit of the Earth around the sun. You have probably heard that the Earth's axis is tilted. But tilted, what do you mean by tilted? With respect to what? Okay. Now we have an idea. We can define it in terms of the ecliptic plane. So here I'm going to draw in a red line representing the perpendicular, the direction perpendicular to the ecliptic plane. This is at a 90-degree angle, a right angle. And what we mean by the Earth's axis being tilted is that if I draw in the equatorial plane, okay, that's I've done in green, the angle between the ecliptic plane and the equatorial plane is, not zero. Okay? The equatorial plane and the ecliptic plane are not aligned. There's some tilt between those two. If you prefer, you could also think of the Earth's rotation axis. The Earth's rotation axis, which is perpendicular to the equatorial plane, okay? The Earth's rotation axis does not align with this dotted red line that I've put in there. Okay? It is angled, it is tilted with respect to the dotted red line. Either one of those will give you the same answer. Now, how large is that angle? So here comes another number at you. Okay? It is 23.4 degrees. Okay? And you'll probably want to have that in your memory banks. Okay? We'll use it a couple times going forward. Okay? Terminology for you. Okay? So this division, this separation between the illuminated side and the dark side. Okay? And this will apply to the moon, it could apply to Venus, it could apply here to the Earth. Okay? That separation between the illuminated and the not illuminated side is called the terminator. I'll be back. Okay? So, and it's the shape of the terminator, for example, that we use to describe the phases of the moon. Crescent, gibbous. Okay. Now, as you see here, because the Earth's rotation axis is tilted with respect to the perpendicular, because of that, I'm going to go back to our Quito-Rowley North Pole example. Okay. Now, I've taken the same figure that we had on the previous page and I have literally rotated it 23.4 degrees. Okay, so I just rotated these three cities 23.4 degrees. Okay. And now here's the question. Which city receives the most sunlight? Yeah, you see it now, right? Yeah, right. Raleigh, North Carolina is actually angled the most towards the sunlight. It is going to receive the most sunlight as compared to Quito or the North Pole. Yes, there are times during the year that North Carolina gets more sunlight than Quito, Ecuador. We've got our handy dandy Earth here. I am going to use this line to represent the equator. Okay? So line represents the equator. Blue, we'll call that the southern hemisphere. Red is the northern hemisphere. Okay? So what happens? Well, we have our Earth. And why don't we go ahead and we'll call you the sun. So I guess I better hold it up here so that it's in the same plane as the sun. Okay? Now notice I've got it tilted just a little bit. Of course, the rotation axis still has it spinning. I'm not going to do that because it's just too hard for me to move and spin and all that kind of jazz. Okay, so you're the sun. I've got my equatorial plane tilted, and I am going to go and orbit around you. Okay. Now, what do you see right here? Okay. Do you see more of the southern hemisphere, or do you see more of the northern hemisphere? Yeah, more of the southern hemisphere. Because of that tilt, as the Earth orbits the sun, there are times during the year where the southern hemisphere is facing the sun and therefore gets more sunlight, warmer temperatures, and we would call that summer. Whereas the northern hemisphere, less sunlight, colder temperatures, and therefore it is winter. But 6 months later, now the north is getting more sunlight. It's a higher temperature, summer, whereas the south, less sunlight, lower temperature, and it's the winter. Okay? And of course, in between, right about here, you get about a 50-50 split. Right? About the same amount of sunlight for the northern hemisphere as the southern one. Okay? And of course, behind the camera as well. Of course, right here between summer in the northern hemisphere and winter in the northern hemisphere, halfway between, fall. Okay? Yeah, good. And of course, back on the other side, spring. Wait, there's more. Okay, that's only half the story. So we have this whammy about getting more sunlight or less sunlight, but there's a second thing that happens due to the Earth's axis being tilted. Okay, so let's go ahead and get that one out of the way. So, question for you. So I've drawn in the axis. I've given you the rotation axis in green. Okay, I have given you the ecliptic plane. That one's in black. And I apologize, but you could imagine the equatorial plane being angled slightly. Here's the question for you. Okay, I have two cities equidistant from the equator. So city 1, city 2, they're the same distance away from the equator. Which city experiences a longer number of hours of daylight? Yeah, you got it? Yeah, good. You say, well, how can I guess this? How can I get this from the picture? Remember that when a city crosses the terminator, it is going from nighttime to daytime. Okay? So, for example, city 1, it's nighttime. Now it crosses the terminator, daytime, and then sunsets. Now it's nighttime again. Okay? So you can kind of see the path, how long that path is. Well, let's look at city 2. City 2, okay, it's nighttime, still nighttime. Okay, daytime, nighttime. Right? Which city, an analogous question would be, which city has a longer path on the daytime side of the Earth? You say, well, city 1. I can see visually how long its path is. It's dramatically longer than city 2. Okay? And again, why does that happen? Because the Earth's axis is tilted. So not only does city 1 get more sunlight, because it's in the northern hemisphere and in the northern hemisphere is facing more towards the sun, but in addition to that, it is also getting a longer number of hours of sunlight. So it's like a double whammy. More sunlight for a longer period of time, as versus less sunlight for a shorter period. Boom, we've got our idea. We have the two effects for why we have summers and winters. Let's go ahead and relate this to geography. Say, what do you mean? Well, here you go. Here is a map of the United States. Here's a political map that I have shamelessly stolen from online. Political map of the world, April 2007. And of course, you're probably familiar with these kind of maps, right? You have things like different countries and latitudes and longitudes. Okay, to be continued on that point. But the thing I'm going to draw in here is the equator. We know the equator as the line that cuts the Earth equally in half. so that you have a northern hemisphere and a southern hemisphere. One of the things that I've always kind of been curious about, and I kind of understood it, but you kind of memorize it, but you don't really think about it. Okay, there's two more lines that generally end up on a map. Okay, and in fact, you can see it. It's right here. This dashed line across the top, and this dashed line equidistant across the bottom. Okay, what are those lines called? Not latitude. I mean, yes, they are a specific latitude, but we give those two lines a very particular name. Yeah, we call them the tropics. Okay? Why do we put these things on a map? Why do we have things like the Tropic of Cancer and the Tropic of Capricorn? What is the rationale for that? Okay? Well, let's go back to our ideas about seasons. So again, I've got, let's say, the Tropic of Cancer. I've got the ecliptic plane. I've got the celestial plane angled like this. Okay? And I've got the sun. Okay, pretty straightforward. Okay. And here's the idea. The Tropic of Cancer is the northernmost latitude where the sun can be seen at zenith at least one day a year. If you are standing on the Tropic of Cancer and you just look up at zenith and you wait, okay? So you spend 365 days, 24 hours a day, just sitting there looking up, okay? There is one day in the year, in fact, it's a very specific instant in time, but there's one day in the year where you will be blinded by the sun. It will pass directly through your zenith. Okay? Now, if you're standing on the Tropic of Cancer here. Okay? Now, if you're standing north of the Tropic of Cancer, how many days will you see the sun pass through zenith? Yeah, 0, right? The Tropic of Cancer is that boundary point. Okay? You can see the sun pass through zenith at least one day a year. Okay? If you are north of the Tropic of Cancer, it doesn't matter how long you stand there for looking at zenith, you will never see the sun pass through zenith. Okay? It will never be directly overhead. Okay? If you're in between the tropics, you'll see it pass through zenith twice a year, and it depends on the days. So of course, artists like to play around with this. Here's one. This is called the Sky Gate. This is over in Hawaii. There's no place in the continental United States that you can actually see this happen. Okay, Hawaii, you never think of Hawaii being that far south, but indeed it is. Hawaii is on the Tropic of Cancer. And so what happens, the Sky Gate, this is an art installation, and it's only, if you look at the shadow on the ground, the shadow of this art installation will create a perfect circle only when the sun is directly overhead. Okay? And so this perfect circle only gets formed at a particular instant in time, noon on, well, this would be called the summer solstice. Okay? So noon on the summer solstice is the only time that this art installation will project a circular shadow. Okay? Of course, other cultures play around with this as well. Okay, so here's Chichen Itza, and I don't think I'm pronouncing that correctly. I apologize. And it's a Mayan ziggurat. Okay, it's kind of like a pyramid, but I ziggurat like a tiered pyramid kind of thing. Okay? And this one has been set up not to project a shadow on the solstice, but I believe this one is set up to project a shadow on the equinox, when the sun is directly up over the equator. Well, what happens? Okay, well, let's see here. You notice that there's this long ramp leading up to the top. Okay? And because of this stepped pattern on the edges of the ziggurat, right, the sunlight hits this, and you notice that the shadow of these sides creates this wavy pattern on the stairwell. Okay? And of course, the cool thing, oh, this is so cool, right? The bottom of the stairs, what do you see right down here? Yeah, it's a snake head. So the idea is on the equinox, you have the body of the snake slithering down the staircase. It's cool, right? Yeah. Okay, yeah. Oh, excuse me. There's the celestial plane. I was wondering where that was. Cool, right? Yeah, okay. So aside from the Tropic of Cancer, that limits where the sun can be directly overhead at least one day a year. Okay. Oh, incidentally, the Tropic of Cancer is how far north of the equator? Yeah, it's that 23.4 degrees again, right? That axis is tilted 23.4 degrees. That means that this Tropic of Cancer is going to be 23.4 degrees above the equator. And similarly, the Tropic of Capricorn is 23.4 degrees below the equator. Okay. Now, the point that I want to draw your attention to is up here, close to the North Pole. Okay. Let's imagine for a second a city. Okay. In fact, I'll draw in the path. Okay. You notice that that city, for that day at least, has a time where it never crosses the terminator. Similarly, if we looked at the southern hemisphere, there's cities, say locations, maybe a better word. There are locations where they never cross the terminator. Okay. So this location, you'll experience at least one day where the sun never sets. It might get really, really close to the horizon, but it'll never actually pass below. Similarly, you'll have locations in the southern hemisphere where the sun will never rise. I wasn't able to find a good photo sequence like that, but here's pretty close. Okay? Where the sun barely peaks above the horizon and then sets again. Okay? And if you go just a little bit further north, the sun would never actually even pop up above the horizon. Well, what do we call these two locations? These defining locations where you spend at least one day in perpetual sunlight, or conversely, one day in perpetual darkness. Yeah. What do we call those? Yeah, the Arctic circles. Okay. Those locations, they're called the Arctic circles. And if we notice, they are still related to that 23.4 degrees. If we take 90 minus 23.4, so we'll take 90 minus 23.4 degrees, you'll end up with 66.6 degrees. And I'll put north here. Okay? What that means, that is the latitude at which you'll have at least one day of perpetual sunlight. Okay? Or conversely, one day of perpetual darkness. Now the bummer is that if you have one day of perpetual sunlight, you're going to pay for it with at least one day of perpetual darkness. Similarly, if you have something like 10 days of perpetual sunlight, you're going to pay for it later in the winter because you're going to end up with 10 days of perpetual darkness. Okay? Or if you have 3 months of perpetual sunlight, you'll get 3 months of perpetual darkness. So there's a trade-off. Kind of a bummer, really. Yeah. Cool, right? And again, that's related a little bit to our seasons. Yeah. So to wrap it all up, okay? When the sun is located above the equator, when the Earth has gotten to a position where the sun is directly above the equator, okay, you'll notice that as the Earth rotates, every location on the Earth is going to get the same amount, I should say, the same number of hours of sunlight when it's directly above the equator. We call that the equinox. It's equal day and night for all. We have 2 times when that happens. Once, say right here, and then again when I orbit behind the camera. Okay. Those roughly occur on March and September 22nd. Okay. And that changes according to our calendar, right? What's the important point is the sun has to be directly over the equator. So we check to see, is the sun above the equator? Nope. How about today? Oh, yep, that's the day. Okay, well, whatever day it is on our calendar, that's the first day of the equinox. Okay? So it's not based on the calendar, it's based on the position of the sun in space. So how about tropics of Cancer and Capricorn? Those are the northernmost and southernmost latitudes where you can see the sun at zenith at least one day a year. Okay? And that day of the year where you see it at zenith on the Tropic of Cancer or the Tropic of Capricorn, that dictates the day, the start of the summer and or winter. Okay? So if it's zenith at the Tropic of Cancer, it's first day of summer for the northern hemisphere. First day of winter for the southern hemisphere, and vice versa. Okay? Those will correspond to the longest and shortest days of the year. And I should be more specific. I should say the longest / shortest hours of sunlight. Okay? So I should say daylight of the year. Those occur roughly on June 21st and December 21st. Again, if you get it in the ballpark, if you say June 20th, I'm okay with that. Okay? So get it in the ballpark, but you should have a rough idea when those are. And those latitudes correspond to 23.4 degrees north and south. Of course, lastly, we have the Arctic circles, locations on the Earth where the sun does not rise for at least one day. You could similarly say does not set for at least one day. Okay? And those locations, you have to be further north than 66.6 degrees north or 66.6 degrees south. Okay? You're basically going to get into Antarctica, or excuse me, not Antarctica for the southern hemisphere, Alaska, Siberia, northern Canada for the northern hemisphere. Okay? Okay. Well, we'll call it quits there. I think we've covered enough ground for today. I thank you for your attention. Keep up the good work. I'll see you next time.